Hello everybody. Today we're going to begin a discussion of the wave nature of light. This is chapter 27. First of all, I hope that you're all doing fine, and I hope that you're paying attention to the health advisory from the university and from the CDC. Let's all try to be safe. You'd recall that in chapter 25, we ignored the fact that light is indeed a wave phenomenon, and treated light as though light travels only in straight lines that we call rays of light. And this is possible because the wavelength of light is so small compared to the dimensions of everyday objects, the physical dimensions of everyday objects. And for that reason, we can essentially ignore the fact that light actually wiggles when it travels, and treat light as though it travels all the time in straight lines. This is the subject that we call geometric optics, because we can use the simple laws of geometry to predict how light will behave when it encounters an obstacle, like when it bounces off a surface, or when it travels through a transparent medium, in which case its path will change. There is a refraction of the light, there's a bending of the light ray, because the light has made the transition from one medium to a different medium. But there are certain applications, certain other situations in which you cannot ignore the wave properties of light. And this is especially true when light is passing through an aperture that has dimensions that are not that different from the wavelength of light, or not much larger than the wavelength of light. And in these cases, the wave properties become very apparent, and this is what we're going to discuss in this chapter. So to begin, let me remind you of what we mean when we say that light is a wave. In chapter 24, we saw that light is a very good example of an electromagnetic wave. So if you remember this drawing, that if you have an electromagnetic wave, i.e. if you have a wave of light that's propagating from a source on the x-axis going from left to right, then if we consider the electric field contained in the vertical plane, then the magnetic field is contained in the horizontal plane. The electric field is always in phase with the magnetic field. You remember this? So, for example, when the electric field is at its maximum, the magnetic field is also at its maximum. And these two phenomena are always oscillating in phase with each other. So the typical drawing that we had to do was a sine wave for the electric field. It's going up and down. And the magnetic field, let me use a different color. So the magnetic field will do something like this. And it's contained in the horizontal plane. And at all times, while they are oscillating, the phenomenon is propagating to the right on the x-axis. You must also remember that the magnetic field magnitude is constantly, at all times, related to the electric field as follows. It's the electric field divided by the speed of light. So as an example, if you suppose that the electric field has a magnitude of 1 volt, let's just use a very simple number, 1 volt per meter, then the magnetic field will be given by dividing 1 by the speed of light, let's assume that it's 3 × 10⁸ meters per second, and this works out to be approximately about, let's say, 3.33 nanoteslas. You can confirm this quite quickly. Which means that when light interacts with an object such as an electron, it's the electric field part of the wave that is going to be dominant. for this reason, for the rest of this chapter, when we draw light as a wave that's propagating, I will not draw the magnetic field component. I will instead draw light simply as a sine wave like this. But you must understand that light is indeed composed of two fields, the electric and the magnetic field, that are constantly propagating. Now, if light is a waveform, then light can exhibit two very important characteristics. The phenomenon of diffraction and the phenomenon of interference. And I'm going to assume that not all of you had a chance to discuss wave propagation in College Physics 1. So we're going to start with a very brief review of wave propagation in general. And I'd like to use the very simple idea of a waveform that is traveling on the surface of water. So if you disturb water by dropping a pebble at one point, then you can disturb the surface so that it propagates as a waveform. So here's an example. Say we have a pond or a lake or a pool of water in a tank, and we're looking from the top of this pool. And say we drop a pebble at this point. Then you see these ripples that begin at the source and travel outwards. And what I'm drawing now are what you would call the front of the wave front. And these propagate away from the source to infinity, or until they encounter an obstacle. Let's suppose that on this pond is a toy boat sitting somewhere here. Then as the wave fronts travel, the boat is not aware of the presence of this wave, so it sits still. It does not do anything. It only begins to do something when the wave front hits it, when the waves arrive at the location of the boat. And then our boat just goes up and down. It just bops up and down. It does not travel forward with the wave. And that should tell us that the wave propagation is just a disturbance of the surface. It's not the bulk water that is being carried forward. It's just the surface under tension behaving like a wave. It's just essentially behaving like a string that you have plugged, and it just goes up and down. The distance from one wavefront to the next wavefront is what, of course, we call the wavelength of the wave. And we will give this wavelength a symbol lambda. Another point before we describe diffraction. You can imagine this. Very far from the source, the wavefronts have become very large circles of very large diameters. So imagine that we're very far away from the source now. So ignore the portion of the region here. So very far away from the source, the diameters are so large that we essentially see the wavefronts as though they were flat, propagating forward. So in fact, I can continue this up all the way up, but I'm just drawing a little portion of it. So the wavefronts have sort of lost their circular nature and appear to be flat or plane. And we call these plane wavefronts. And for a lot of the discussions in this chapter, we shall assume that we're so far away from the source that the light wave that we're dealing with comprises plane wavefronts only. So this is the picture that you would see if you were to look from the top, on top of the pond. But if you look at the side, if you look at the wave propagation from the side, so if you set your eye here and look at what's happening to the water, you just see the surface going up and down and so on. And this is the wave that is propagating. This is the crest and this is the trough. and the surface is just disturbed, and this front just propagates on and on. So in this chapter, we have two ways of representing a wave. We shall either represent the wave as a propagating sine wave, or we shall use the wave front to represent the wave. Light is a wave phenomenon, so everything that waves can do, light can do. So this is a very good review for those of you who did not get a chance to discuss the propagation of waves in College Physics 1. Now, as I said a minute ago, there are two things that waves can do. And these two things are diffraction and interference. And let's take each of them one at a time and explain what we mean by this. Suppose that you have waves in, imagine a very large tank, but the wall of this tank has a hole cut into it like this. And we have a wave that is propagating forward. So let's say we created a wave from a source that is very far away, and so that we have plane wave fronts approaching this hole or aperture. But now let's draw the wave fronts in such a way that the wavelength is much smaller. The wavefront is much smaller than the size of the aperture. And then see what happens. Well, nothing interesting happens. When the wavefronts arrive here, they simply just pass through. Except that the ends here, the region beyond the hole, appears a little curved. But otherwise, the wavefronts just go on with the same wavelength and the same speed and go forward. If we set our toy boat here in the region that is in the shadow of the wave, it does not do anything because it does not see the wave. So we shall describe this region here as the shadow region. And the wave does not go there. The wave just simply travels on with the same wavelength as before. This is true for a large aperture. And by large aperture, I mean an aperture that is much greater than the wavelength of the wave that is propagating. But we get a very different result when the size of the aperture is small, when the size is comparable to the wavelength of the wave. So now we have the same tank, but now the aperture is very small. The size of the aperture is small, of the order of the wavelength of the wave. In this case, well, here are the wavefronts that are approaching the aperture. But when the wave attempts to go beyond the aperture, it does not do what it did in the case of the large aperture. Instead, what we find is that points along this last wavefront become sources of wavelets, new waves that propagate as if the wave had begun here. So as if this point here was itself the original source of the wave. This time, our toy boat does not sit still. As the wave passes, it bops up and down. This phenomenon is described as the diffraction of a wave. This is diffraction. So diffraction essentially is the spreading of the wave to the shadow region. So this area here would be the geometric shadow region, but in fact the wave can spread to this region here. So we shall define diffraction as follows. Diffraction is the spreading of a wave to the shadow region when the wave passes through a small aperture. But it's not only when a wave passes through an aperture. If a wave passes around an obstacle, diffraction can also occur. So we shall say that it passes through a small aperture or around an obstacle. This can be very easily demonstrated using water waves in a tank. But as we shall see in a minute, light diffracts when it goes through an aperture that is very small or when it passes around an obstacle. Next, let's look at interference. And once again, I'm going to use the example of water waves inside a tank. So now imagine that instead of dropping one pebble at a point, we drop two pebbles. So we're going to drop a pebble here, and we're going to drop a pebble here. Let's call this pebble dropped at point A and pebble dropped at point B. So clearly, we're going to have waves that propagate outwards from pebble A. Let's use the green to indicate the waves that are going away from source A, and let's use the blue to indicate the waves that are going away from source B. And these waves that we have generated have the same wavelength. Each of them is radiating outwards. This is going here. So at some point, they're going to pass over each other. By that I mean wave A, let's draw a few more of the wave fronts. And wave B also does this, and it's moving forward. Question is, what then happens as these waves pass over each other? Well, what happens is simple but also complicated. Complicated in the sense that you have an infinite number of possibilities. But we're not going to discuss all of them. Obviously we cannot. We're going to only discuss the most important possibilities. And essentially there are two main possibilities. The first one is when the crest of wave green, the crest, this is the crest, this is the trough, when the crest of wave green coincides exactly with the crest of, so B is coming here, coincides exactly with the crest of wave B, and these two pass over each other when the crests meet. So when the crests meet, if they have the same wavelength, you can imagine as the crest meets the crest, trough meets trough. And so the two waves add up and build on each other. And so we call this constructive interference. And here's a very simple sketch. So here is wave A, and here we have wave B. And because they are passing over each other, so let's draw wave B. And they are in phase because the crests meet and the troughs meet at the same time. When these two waves pass over each other, they add up to give a larger wave. I can now draw in red. So this is now the larger wave. So we just add the waves up algebraically. This is called constructive interference. It happens with waves, i.e. the tsunami of several years ago that hit Japan, built up waves add on top of each other. You can build a very large wave from a combination of smaller waves. But this phenomenon also happens with light. And when two light waves pass over each other constructively, then you get a net effect that is brighter than what you started with. The other extreme is what happens when this is wave A, but now wave B passes over wave A, the cross, in such a way that when the crest of wave A is passing, it meets the trough of wave B. And as I said, this is a simple algebraic sum, so we're going to add a positive to a negative, so let's assume that they have the same magnitudes, positive and a negative, so we're going to end up with 0, nothing. So in that case, the result is nothing. And this is described as a distractive interference. Distractive because the two waves essentially cancel each other out. Water waves do this, and when you get distractive interference, that means the surface of the water just sits still. It does not bob up and down. Light can interfere distractively, in which case there is no light, i.e. darkness. You have darkness. Okay, so all waves, and in fact all waves do diffraction and interference, and a very good test to see whether a phenomenon is a waveform is to see whether it can diffract and interfere. We shall now discuss a very important experiment that was performed by an English scientist that showed beyond any reasonable doubt that light is indeed a wave. Young's double-slit experiment. In 1801, this English scientist called Thomas Young performed the following experiment. And I'm going to describe the experiment as though we were doing it today, okay? So I'm going to leave out certain details that he did. But essentially, his experiment was as follows. So Young takes, if you wish, a card. And in this card, he cuts two very tiny slits, very tiny holes, rectangular holes, if you wish. They're actually much closer than I have made my diagram look, and also the slits are actually quite thin. But for the purpose of discussion, let's pretend that this is what we have. So this is a slit, this is another slit. And he argues as follows. Let's put a viewing screen behind the slit assembly. My lines are not very straight. Okay, let's draw this properly. So this here is a screen. And then he proceeds to shine light onto the slits. If light travels as rays, a whole bunch of particles that stream forward, if light travels as rays, then we would expect to see the following. Well, light will go through this hole, and so we should be able to see a patch of light right here. And then we should see another patch of light right here. This is what you would expect to see if light is a wave. But this is not what he observed. So let's make the point here. This is as expected or as predicted by ray optics. Ray optics is what we did in chapter 25. Okay. This is not what he observed. Instead, this is what he observed. So this is the viewing screen. We draw a line right between the slits all the way here. So the shadow region, right? There should not be any light there because there's a piece of card that blocks the propagation of the light. But instead, Young's observation was that where we would expect that there would be no light at all, in fact, was a patch of light, very, very bright. And not only that, adjacent to this bright patch was another patch. And then on the other side, there was another bright patch. And that's not all, though. There were more. Another one here, and another one here, another one here, another one here. And of course, the intensity of the brightness of these is getting smaller and smaller as you go away from the central portion. This is what was observed. There's absolutely no way light can produce this phenomenon here if light propagates as rays. The only way this can be observed is if two things happen. Is if initially the light, and I'll show you in a minute using a diagram, is if initially the light going through the slits diffracted and then interfered with itself and formed constructive interference. These are the bright regions, and then distractive interference, the dark portions. So let's demonstrate this now, and then we shall derive a very simple equation that can help us solve a whole bunch of problems. So here is a good explanation for Young's double-slit observation. So I'm going to draw this now looking from the side. So let's say that this is our slit assembly. Drawn from the side. Okay, we shall label this slit S1 and slit S2. Now, of course, if light is a wave phenomenon, then we would expect that the light will come in as wave fronts, which then hit the slit. And as we discussed before, from slit 1, we're going to end up with a diffraction of the wave. The wave goes forward as if the slit were the source of the waves. And similarly, a portion of the same wave goes through S2 and diffracts. And you can very easily see that, yes, indeed, these waves pass over each other. And wherever a crest meets a crest, let's draw a few more of these. Wherever a crest meets a crest, there's going to be constructive interference. And wherever a crest meets a trough, the waves are going to cancel each other out, and we're going to end up with destructive interference. So here's an example. Look, this is crest meeting a crest meeting a crest, crest meeting a crest, and so on. So if I had drawn this properly, if you put your viewing station right here, if you put the viewing screen here, then you're going to end up with bright, 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 and in between a crest and another crest is nothing. That's a trough. So where a crest passes, consider this little portion here, where this crest here passes over the nothing, the trough, that's going to be the destructive interference. And so there'll be another bright, 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 and in between them, you're going to end up with a destructive interference. So this is absolutely convincing evidence that light is a waveform. It's interesting that when James Clerk Maxwell, whom we discussed in chapter 24, did the calculations to show that light is a waveform, in his time, many scientists did not believe him. And it was in 1801 that Young proved beyond every reasonable doubt with this very simple but intelligent explanation. Okay. Next, we're going to look at the details and write a very simple equation to help us solve little problems that involve Young's double-slit experiment. So here are the details. Before I erase this, I should have reminded you that along the central line where we expected a complete shadow, we actually got the brightest patch of light occurring. We're going to explain that now. So I'm going to call this case I and say this is the bright central maximum. And it goes as follows. Consider our two slits. And let's draw a line and set our viewing screen here. So this is our screen. Let's call this S1 and this S2. The distance between slit S1 and slit S2 we shall call D, little d. Please use little d for the distance of separation between the two slits, because later in this chapter we shall use uppercase D to represent the size of the slit, the actual size of the slit. We're not there yet. Use little d to represent the distance between the slits. And this midline that we have drawn here, let's label that angle theta equals 0 degrees. So if we want to describe any angle set by this arrangement, we shall determine it by measuring it with respect to this central line. Okay. Clearly, if the light wavefronts were to appear, let's just draw it as a, okay, never mind. So the wavefronts come in here, and then there's diffraction here, and there's another diffraction at S1, and these travel forward and interfere with each other. So I can draw the details like this going forward, but it's easier to use the representation of a sine wave. So I'm going to instead draw that the wave, let's say the waves began on a crest, and then the wave is going to travel from here to this point here. So let's be guided by this. So the wave does this until it arrives here, and this wave does that. Clearly we're going to get a bright fringe here because we have an equal distance from slit S1 to this point as we do from S2 to this point. The waves are traveling an equal distance. So if at the location of the slits we had a crest and a crest in phase, right? Because they're on the same wavefront, then if they travel the same distance, they're going to arrive as crest. So at this point, one crest from S1 is going to meet another crest from S2, and so we'll have constructive interference. Constructive interference means that we're going to end up with a bright rectangle of light. And this, as I said earlier, is the brightest, and it's usually described as the central maximum. Let's consider some other angle, not 0 degrees. So this first one here applies to the case where the angle theta is 0 degrees. Let's consider some other angle. Some other angle theta that is not 0 degrees. And so this is the arrangement of the slits. This is our midline. This is our screen. Oh, by the way, we shall call the distance from the slit assembly to the screen uppercase L. So once again, this is slit S1, this is slit S2. Let's pick any point such that the angle that the line makes when we draw this line here, let's put this here, is some angle theta. And it's measured with respect to 0 degrees, like that. Let's call this point here point A. But now you can clearly see that the wave that's going to go forward as a diffraction from point S1 is going to travel a slightly shorter distance than the wave from S2, because geometrically you can see S2 is farther from point A. So this wave will begin as a crest and arrive here, and there's another wave that's going from here, and it's going to go, oops, let me draw the wave properly. You can just draw a straight line, just get a ruler and draw it, okay? Clearly they travel different distances, and the fact that they travel a different distance means that what happens at point A will depend on the details of how the waves arrived. Once again, there's an infinite number of possibilities, or a very large number of possibilities. We shall examine a few of them. So let's continue here. And I'm going to erase this because we're very clear on how we obtain a central right fringe. Now consider this situation here. Let's just make things simple. Let's draw 3 or 4 waves, or maybe 5 waves traveling from S1 to point A. Okay, so if this is the wave that is traveling from S1, it starts off as a crest. So this will be 1 wave, 2, 3, 4. 4 is enough. We can use 4 to do this discussion. So after traveling only 4 waves, this wave has hit point A. It hit point A, let's say, as a crest. Now consider wave S2. And remember that the wave from S2 is traveling a longer distance. So the wave from S2 began at the same time as S1, began as part of the same wavefront. So this is the crest. So this is wave 1, 2, 3, 4. But because it has to travel a longer distance, when it gets here, it's not at point A yet. It's not there yet. It has to travel some more. But here's the interesting thing. Suppose that it traveled 1 full wavelength before it hit point A, then you could not tell the difference because it will still arrive with a crest. And crest meets crest will give you bright. Or 2 waves, or 3 waves, or 4 waves before. So if this is lambda, and this is another lambda, and this is another lambda, and so on. So what I've described here, it takes, or it took 3 waves before it arrives. 3 extra waves before it arrived at point A. You still cannot tell the difference because either way, it's going to arrive with the crest. So as long as the path difference so let's say if the path difference is 0 lambda, which is 0, 1 lambda, 0 lambda means there's no path difference, and there's no path difference. Or if the path difference is just 1 wavelength, or 2 wavelengths, or 3 wavelengths, you're still going to end up with the same constructive interference. and therefore you get a bright construction of the wave. But what if the wave from S2 had to travel only half a wave before it arrived at point A? Then, in doing so, it arrives with a trough. And remember, when a trough meets a crest, this is negative, this is positive, they're going to cancel out, and you're going to end up with 0. So, if the path difference is 1/2 of a wavelength, or, so this is 1/2, this will be 3/2, 5/2, 7/2, and so on. So 3/2 or 5/2 or 7/2, and you can, let's stop it, we've made the point. If this is true, then the wave from S2 is going to arrive as a trough. It's going to cancel out the crest, and you'll get nothing. Nothing means you get a dark patch. So, mathematically, we can put this together very nicely. We can say the following. The path difference is, so if the path difference is m times lambda, where m is either 0 or 1 or 2 or 3 or 4, there's a whole number counter, then we're going to end up with bright. But if the path difference is m plus 1/2 of lambda, then we're going to end up with a dark fringe. We're done. Now all we have to do is to write a simple expression for the path difference, and then we are ready to do some problems. So let's do that now. And it's a good thing that I left this diagram on. So the path difference between these two waves is just this little portion here. Just this portion here. This is the difference in the path length. But in trying to get this little distance here, we have to use some approximation. We have to cheat a little bit, because this is a triangle, and this extra length is geometrically, we can calculate it, but we can use an approximation. We shall assume that since the length L is very large compared to our setup here, then we can draw the waves as follows. We can just say this is going out like this, and this is going out like that. And remember that this angle here is theta. So like parallel lines, so that the calculation becomes easier. In that case, the path difference is this little portion here. And if this angle is theta, then this angle is theta as well. Of course, this is 90 degrees because we have chosen these, we have approximated these to parallel lines, so this is 90 degrees. And don't forget the distance between the fringes, that's D. So if I pull out this little triangle here, then we have the following. This is our D, we have an angle theta here, and then we have this right angle here, and this is the path difference that we're trying to calculate. This path difference here. So Katoa comes in, right? This here is the opposite to the angle. Opposite goes with sine. So the path difference we can write very quickly is simply d sine theta. We're done. So to summarize all this, we write a simple equation for Young's double-slit experiment as follows. If the path difference d sine theta is m times lambda, we get a bright patch of light. On the other hand, if d sine theta is m plus 1/2 times lambda, then we end up with a dark patch of light. The patch of light is actually called a fringe. So this top one gives us a bright fringe, and the bottom one gives us a dark fringe. Okay, and this is the simple equation with which we can do a whole bunch of problems. All right, let me say one more thing. The bright fringes are often described also as maxima. They are maxima because there's one wave adding up to another wave, so you get a maximum. And the dark fringe is described as a minimum. So these will be the minima. And because there's nothing, so it's at the lower end. These are the minima. So, okay, so at this stage, we have enough information to do problems. So I'm going to do a couple of problems from the Open Stats textbook. And this is from page 1099, page 1099 of the Open Stats textbook. And we can begin with question 6, which says the following. At what angle is the first order maximum? My equation is complete, but I need to give you some terminology. M, you recall that M takes on the values of 0, 1, 2, 3, 4, 5, 6 whole numbers. Okay. M is called the order of the fringe. The order of the fringe. So as an example, M equal to 0 we shall describe as the 0th order. M equal to 1 we shall call the first order, and so on. M equal to 3 we shall call the third order. You get the idea. So this is the language we shall use when we're doing these problems. So it says, at what angle is the first maximum, is the first order maximum? For 450 nanometer wavelength blue light. That's fallen on double slits separated by 0.0500 millimeters. Okay. At what angle is the first order maximum for 450 nanometer wavelength blue light? That's fallen on double slits separated by 0.0500 millimeters. So let's pick out the key data that's given to us. First of all, it says at what angle? So we need to be finding theta. At what angle is the first order? That means our M is 1. We're working with the maximum. So that means we will be using the equation for the bright fringes, the maxima. So the correct equation would be d sine theta is m lambda, where m takes on the value of 1 in this case. The wavelength of light is given to us, so that's lambda is 450 nanometers. And the slit separation, the two slits are separated by 0.0500 millimeters. So that's little d. So d is 0.0500 millimeters. So as you can see, this is not a particularly difficult problem because the equation is quite straightforward. Well, let's write out the equation and put in the numbers and proceed to solve the problem. So d sine theta is m lambda. D we're given. Please, it is important that when you do these problems that you convert all your numbers into SI units. Otherwise you're going to mix things up and get the wrong result. So our D, as a matter of fact, let's continue on this side of the board so we can do things better. So D is 0.0500 millimeters. So that's 0.0500 10 to the negative 3. That's 0.05 millimeters. We're going to multiply this by sine theta, and the theta we do not know, but we set this equal to m is 1, then times the wavelength. The wavelength is 450 nanometer. Nanometer is 10 to the negative 9 meters. And then we proceed to solve for sine theta. So sine theta is 450 10 to the negative 9 divided by 0.0500 10 to the negative 3. We can do some quick math to simplify this. The top is 4.50 10 to the negative 7. And the bottom here is, as you can see, 5.0 10 to the negative 5, which gives you 4.50 divided by 5.0 10 to the negative, what is it, negative 2. This is 0.9. 4.5 divided by 5, this is 0.9 times, so this is 0.9 10 to the negative 2, which is 9.0 10 to the negative 3. You can check this yourselves. So that is our sine theta. That is not our theta yet, that's our sine theta. And from that we do the sine inverse. So theta will be the inverse sine of 9.0 10 to the negative 3. And I have my calculator handy, so I shall go ahead and do this. 9.0 to the negative 3. And then we proceed to find the inverse sine of that. And that's a very small angle actually. That gives us 0.51566, because we shall, well, remember that if this were Quest, on the Quest website you will enter as many numbers as possible. So let me go ahead and write out the full 669. 2, 3 decimal, so 366, we can write this as 0.516 degrees. That's our angle. And as you can see, the angle is very small. And that's probably because the distance from the slit assembly to the location of the viewing screen is quite long. So the first order, which is the fringe that is right adjacent to the central bright maximum fringe, makes a very small angle with the central line. I will do a few more solutions and post them on Blackboard, but let's do another example, and this will be the end of today's lecture. So I'm going to go ahead and erase this and write out another question. Let's do question 8, which says the following. What is the separation between slits? So now we're asked to find little d. What is the separation between two slits for which